Hi, George Diamond here. Today we're going to take a look at video number 2 on the second derivative test. Now this is the video where we look at some examples. Alright, now in our first video we defined concavity. We looked at the relationship between the second derivative and the original function. Because remember, the second derivative now describes the concavity of the original function, whether the original function is concave up or concave down. We also defined and looked at the inflection point. Now we didn't look at any examples where we actually had to find the inflection point, and we in the first video. In the second video we will. Also in the second video here we're going to look at some examples of how to use the second derivative test to identify and locate any relative maximum or minimums on our curve. So it'll do the same thing that the first derivative test will do. Okay, so this is in our textbook, this is section 3.4, and once again this is video number 2. This is the video where we actually do some examples of what we looked at in the first video. Now, our first problem, I'm going to take this down in just a minute, so if you want to copy the problem down, you can. So we're going to determine the open intervals on which the graph is concave up or concave down. I'm going to start off with an easy one. This is just a little polynomial function, so we'll look at some more difficult problems later. Let me erase this. Now, so where's the graph concave up or concave down? Right, so concave up or concave down. All right. Now our function, we have f of x is equal to, and this is problem number 1, so f of x is equal to x to the 5th minus 5x, okay, plus 2. All right. Now I'm going to take this down. All right, so give me a little bit more room to work. Right, so to get started, to begin with, now I said to determine where the graph is concave up or concave down, remember the second derivative tells us the concavity. So first thing we're going to have to do is we have to figure out what the inflection points are. So we've got to get the inflection points. All right. Now, you got to remember now, inflection points are where the second derivative is equal to 0 and where the second derivative does not exist. All right, so this is what we're going to have to find here in this problem here. We got to find any inflection point or inflection points. There could be more than one. And those occur where the second derivative is equal to 0 and where the second derivative doesn't exist. So we're going to get the second derivative, so let's go and get the first derivative. All right, so the first derivative here would be 5x to the 4th minus 5. All right, the second derivative. So let's go ahead and get the second derivative while we're at it. All right, the second derivative would be 20x. So this is our second derivative. Okay. So as we get started, remember now we're looking for the where the graph is concave up or concave down. So to get our inflection points now, so we need to decide where the second derivative is equal to 0 and where the second derivative does not exist. All right, now one thing I want to point out, I didn't do this in the at the beginning of the problem, but you always want to start off by looking at the domain of the original function. Right, in this case here, the domain of our function is all real numbers, so all reals. So this is a polynomial. Polynomials are defined everywhere, so any inflection point would be, any number, any x value we get for an inflection point here would be an actual x value for an inflection point. Also, okay, this is a polynomial, so it's defined everywhere. There are no places where it doesn't exist, but you got to check. If radicals or fractions, you have to watch out. So this is a little polynomial, so we don't have to worry about that. Okay, so let's find the zeros of the second derivative. So take your second derivative, so 20x, set this equal to 0, and then solving for x, just divide by 20, x equals 0. So this problem, we have one inflection point. So one inflection point. All right, so actually it's not a point, it's the x value of the inflection point. Now to get the y value, I'm not going to get the y value, but to get the y value, you'd have to take this x value and plug it back up into the original function. So let's see. Now what I'm going to do, I'm going to put the x equals 0. I'm going to fix me up a little number line. I'm going to put it on a number line that kind of describe the relationship between the second derivative and the original function. So it's just a little number line here. So like what we would do with the first derivative test, all right, but this is just the second derivative. Okay, just put the inflection point on our number line. Okay, up above, let's describe the second derivative, and this will be the function itself. All right, remember now x equals 0. Okay, this is an inflection point, or an inflection number, if you will. Okay, it's not the actual point, but an inflection number, right? Okay, this is where the concavity of this graph changes. The only problem is, right now, we don't know whether the graph is going to be concave up to the left of 0 or concave down. So we're going to pick us out a test value, and we're going to substitute it into the second derivative now. Because remember, the first derivative tells you whether the graph is increasing or decreasing. The second derivative tells you the concavity. Is it concave down or concave up? So the second derivative tells you the concavity. So let's pick us out a couple of test values. I'm going to try -1 and +1. So we'll try some number to the left and to the right, and let's see what we get. So this is an inflection number, if you will. Okay, try the -1 first, and we're going to substitute this into the second derivative. So the second derivative at -1 would be 20 times -1, which is -20. Now, keep in mind, the actual number doesn't matter. The only thing that matters here is the fact that it's negative, right? Because that tells us that the second derivative is negative. So from -infinity to 0, then the original function has to be concave. So concave down. So concave down. Okay. Now let's do the second derivative at 1. So let's see if it's concave. It should be concave up on the other side, but let's just substitute it in to make sure. So the second derivative at 1 would be 20 times 1, okay, which is +20. And remember, the actual number itself doesn't really matter. All that really matters is that it's positive, so the second derivative is positive. Okay, that means it's going to be concave, okay, up on the other side of 0. So now we're looking for the intervals where it's concave up or concave down. All right. So let's see, it's going to be concave up. So concave up and concave down on the following intervals. So from -infinity to 0, the original function should be concave down. So from -infinity to 0, and then from 0 to +infinity, the graph will be concave. Let's see, I got those reversed, didn't we? Hold on. Let's see, erase that. It's going to be concave up where the second derivative is positive. So that'd be from 0 to +infinity. So 0 to infinity. And then from -infinity to 0, the graph will be concave down. So we're just, all we had to do with this particular problem, we just had to find where the graph is concave up or concave down. Now to get that, you have to find, remember, you have to find the inflection point first. That's where the concavity changes. And then we can just pick us out a little test value to the left and right and test it in the second derivative, and that tells us whether the graph will be concave up or concave down. Now remember, you want to use the second derivative to tell the concavity. If you substitute it into the first derivative just tells you if the curve is increasing or decreasing. So you want to use the second derivative there if we need to look at the concavity of the function. Okay, let's try another problem now. Okay, this particular problem here, we're just trying to determine the intervals where the graph is concave up or concave down. All right, let's try problem number 2. So problem number 2, here we go, let me set this up. This time it says we want to look for the inflection points and discuss the concavity. So I say discuss the concavity, I guess that would indicate the intervals where it's concave up and concave down. And we're going to try to find the inflection points too. All right. Now, the first problem was a fairly simple problem. It was a little parabola. Now, this one's a little bit more complicated, all right? So this is going to be kind of a long problem, so make sure you got some room there to work this problem out if you're writing it down with me or working it out with me. All right. So to get it started, let's go ahead and write this problem. Now we got number 2, and we're looking for inflection points. So inflection points. So actually now we're going to get the inflection number. We're not going to get the actual y value. We're going to find the x value only, then you can get that yourself by substituting it back up into the original function. Now our function here, we've got f of x equals x times 9 minus x to the 1/2 power. So that radical, let's go and rewrite that in rational exponent form. Because we're going to have to take the derivative of it here in just a second, all right? So convert it to rational exponent form. Okay, and we're going to find the inflection points, and we're going to describe the concavity. Okay, so we're going to describe the concavity too. So here's our problem. So let's get started. We're going to have to find the first derivative. Now, one thing about finding the inflection point, one bad thing, you got to get the second derivative, and that means finding the first derivative. Now, if the first derivative is kind of hard, the second derivative could be twice as hard. So let's see what we get for the first derivative. Now, you have to recognize here when you look at the problem, x times the square root of 9 minus x. Now, this is a product. Right, so this is x times that radical. This is a product. So when we take the first derivative, we're going to have to use the product rule. Right, so you got to recognize that this is a product now. A linear function times a radical. So you got to use the product rule as you find the first derivative. So let's get started. Let's see what we get for the first derivative here. Right. Then after that, we got to find the second derivative. So let's see what we get for the first derivative. So the first derivative is going to be the first times. Now, as you take the derivative of 9 minus x to the 1/2 power, remember you're going to have to use the chain rule. So the derivative of the outside, bring the inside down, times the derivative of the inside. So this will be 1/2. 9 minus x to the, now you got to subtract 1 from your exponent here, so it'll be to the negative 1/2, times the derivative of the inside, which is negative 1. So that's going to be the first times the derivative of the second, plus the second, which is 9 minus x to the 1/2, times the derivative of the first, which is 1. All right, so this is the first derivative now. All right, now we found the first derivative. Now we're going to have to simplify this a little bit so that we can get the second derivative now. Second derivative is what we really need here. So we're going to get the inflection point. That's where the second derivative is equal to 0. So we're going to have to get the second derivative now. And that means, let's see if we can simplify this a little bit. And let's see what we get as we simplify now. This is the first derivative. So let's see what we'll simplify here. We're going to rewrite this without the radical. This is a negative 1 times x will give us negative x over 9 minus x to the 1/2 power. 9 minus x to the 1/2 power. Plus 9 minus x to the 1/2 power here. All that over 1. Now we're going to have to add these two fractions together. Now we've done this before in some other problems. So this type of problem, you got to be able to add these two fractions, if you will. Okay, that means getting the same denominator on both. So let me see if I can remove our problem here. Give us a little bit of room. All right. Now we're going to multiply the bottom of the fraction by 9 minus x to the 1/2 power. So 9 minus x to the 1/2 power. And let's see, now there should be a 2 in here too. Let's see, this is negative 1, so there should be a 2 on the bottom of our fraction here. So it'll be 2 here. All right, so this will be 2 times 9 minus x. It'll be the 1/2 is on the bottom of your fraction there. So it'll be on the bottom of the fraction with the 9 minus x to the 1/2. And then you end up with x times negative 1, gives you negative x, that'll be on the top of your fraction. All right, now let's see, so for our least common denominator, then we have to multiply by 2 times 9 minus x to the 1/2. Now you got to multiply to the top also, so 2 times 9 minus x to the 1/2 power. So whatever you multiply to the bottom of the fraction, you got to multiply the same thing to the top, so to the 1/2. Okay, now once again we're getting getting our first derivative, so we're going to add these together. So as we combine these now, this gives us negative x over 9 minus x to the 1/2. Okay, plus this would be 2 times 9 minus x to the 1/2. Now as you multiply the 9 minus x to the 1/2, remember you're going to add your two exponents here. It will give us 2 times 9 minus x to the first power, or just 2 times 9 minus x. Now, let's remove our parentheses, combine like terms now. Let's see what we get here. This is 2 times 9 minus x to the 1/2. And this gives us what? Negative x plus, so negative x plus 18 minus 2x. So multiply inside of our parentheses. And let's see, we got a combined like term. We have a negative x and a negative 2x. Now that'll give us 18 minus 3x on top, divided by 2 times 9 minus x to the 1/2 power. Okay, that's our first derivative. Okay, that's how the problem starts. Said, you know, the one bad thing about, you know, this type of problem, you got to find the second derivative. So you got to be real careful, watch your signs and things. You got to add those two together now. Now, to get the second derivative, we're going to have to use the quotient rule now. So I'm going to have to erase where I just calculated, give myself some room here. It takes a big part of my board. So let me erase this part right here where I found the first derivative. So let's erase here. Now, so this is the original problem. This is the first derivative. 18 minus 3x over 2 times 9 minus x to the 1/2. Right? So this is the first derivative now. Right? So we've got our original function and the first derivative. Okay, now to get the second derivative, we have to use the quotient rule. All right. So let's see what we get in the quotient rule. So the second derivative will be. So remember how the quotient rule starts. This will be 2 times 9 minus x to the 1/2 power. So you're going to take your denominator and square it. All right, and we'll take the bottom, which is 2 times 9 minus x to the 1/2. So the bottom, so 2 times 9 minus x to the 1/2 power times the derivative. So see the bottom times the derivative of the top. Now the derivative of 18 minus 3x would be negative 3. Okay, minus the top, which is 18 minus 3x, times the derivative of the bottom. Okay, now as you take the derivative of 2 times 9 minus x to the 1/2 will give us 1/2 times 2 is 1, so that would just be 9 minus x to the negative 1/2. So take the derivative of the outside, bring the inside down. So remember 1/2 times 2 is 1, so that would be 1 here. Times 9 minus, bring the inside down, don't do anything to the inside, times the derivative of the inside, which is negative 1. Okay, this is the second derivative. All right, now remember the second derivative, you know, actually getting the derivative is usually the easy part. Okay, now we got to simplify this expression. Remember now we're looking for the actual inflection points. This is where the second derivative is equal to 0. So right now we're going to have to simplify this a little bit. Okay, let's see if we can clean it up some. Now to simplify this, we've got 2 times negative 3 will give us negative 6 times 9 minus x to the 1/2. Okay, now here we've got a minus times a negative 1. Make this plus. All right, so change that to a plus. And let's see, what do we have now? It'll be plus 18 minus 3x times 9 minus x to the negative 1/2 power. All this divided by, on the bottom here, 2 squared gives us 4 times 9 minus x to the first power. 1/2 times 2 gives you 1. Okay. All right, now let's see, we're going to simplify this a little bit further. Let's see, let me erase this, that's our first derivative, all right, so we got that. Now, to simplify this expression, here's our problem, all right? There's several ways to do this, but this is the way I like to simplify this. The exponent of negative 1/2 here is the problem as far as simplifying this. We're going to have to rewrite this so that it doesn't have this negative exponent in our numerator. Right, so now, remember how we're going to do this. We're going to multiply the entire numerator by 9 minus x to the positive 1/2 power. Now, if you multiply that to the top, then you got to multiply 9 minus x to the 1/2 power to the denominator also. So we'll multiply to the numerator and the denominator. Okay. So we know what we have to do now to get rid of the negative exponent. So what will happen? When you add the negative 1/2 and the positive 1/2 together, is going to add up to give you 0. So let's take and multiply the 9 minus x to the 1/2. Let's multiply over here first. And that'll give us negative 6 times 9 minus x to the 1/2 plus 1/2 gives you to the first power. Okay, plus, and this will be 18 minus 3x times 9 minus x to the, add the negative 1/2 and the 1/2 together, multiply it here, gives you to the 0 power. All this divided by, now as you multiply here, will give us 4 times 9 minus x to the 1 plus 1/2 gives us 3/2. So that'll be to the 3/2 power. So that'll be the denominator here of the 9 minus x in the denominator. Now keep in mind, 9 minus x to the 0 power is actually 1, so that basically that gets rid of that expression there. So that whole thing, I'm just going to erase it. Now, all that's left to do now is to remove parentheses, combine like terms, and let's see what we get here. So let's see if we can simplify this some. This will be 2 times 9 minus x to the 1/2 on the bottom over fraction still. Multiply the negative 6 inside our parentheses will give us negative 54 plus 6x plus 18 minus 3x, and that'll be equal to, and once again we're still simplifying here. This is 2 times 9 minus x to the 1/2 power. Okay, on the bottom of our fractions, actually it'll be 4, I'm sorry. So it'll be 4. So make that change here, so it'll be 4 times the quantity 9 minus x to the 1/2. Now let's combine like terms in our numerator. That'll give us 6x and 6x minus 3x is 3x. And negative 54 plus 18 gives us negative 36. Okay, negative 36. Okay. Finally, we got the second derivative. All right. It was even harder than getting the first derivative. You had to use the quotient rule here, so it's just kind of tough getting the second derivative. All right. Okay, now we're ready to get our inflection points. Finally. Now I'm going to have to erase everything that I did here and let me write our second derivative over here. So erase this right here. Okay, we got our first derivative, we got our second derivative. All right. Now, so the second derivative is, so it'll be 3x minus 36 over, over 4 times 9 minus x to the 1/2 power. All right. Okay, so we got our second derivative. Now, one thing I didn't do, and I just now remembered it. One thing that we should have done at the beginning of the problem is to check the domain of the functions. Let's check the domain. All right, now the domain. Now you look at the original function. The original function has a radical, so the radicand underneath the radical can't be negative. So to get our domain, we're going to have to do 9 minus x has to be greater than or equal to 0. It can be 0. And it has to be positive. So it's a square root, so the radicand cannot be negative. Now, solving this for x will give us negative x greater than or equal to negative 9. Positive x will be less than or equal to 9. So, all right, so we know what the domain is. So the domain has to be x. So the domain has to be x less than or equal to 9. All right, so as I look for inflection points now, any inflection x value bigger than 9 won't work. It's outside our domain. So what that means is if you were to look at the graph of this function, if you were to look at the graph, the graph may do, now once again, I don't know exactly what the graph looks like, but I do know, so this is 9, it doesn't exist past 9, all right? So this graph may do something like, something like this maybe, all right? So something like that. So it doesn't exist to the right of 9. So, there can't be, so 9, really 9 cannot be an inflection point, right? Because for that to be an inflection point, the concavity actually has to change. All right, and so really it would have to be anything, 9 could not be an inflection point, and anything bigger than 9 could not be an inflection point. All right, now here we just have to find any inflection points and describe the concavity. So erase this. This is not the actual graph, so this is, but I'm just kind of envisioning what the graph might look like. All right. All right, now to get our inflection points, all right, so we get our inflection points, this is where so what I'll call the inflection numbers. Okay, this isn't the actual points, all right, so to get the actual points, you got to substitute the inflection numbers, the x values back into the original function here. But, so this will be where the second derivative is equal to 0, and where the second derivative does not exist. So let's see where the derivative doesn't exist at. Now, the second derivative is a fraction, so let's take the denominator. So 4 times 9 minus x to the 1/2 power, and let's set that equal to 0. So we're going to find the zeros of the denominator. All right, so this will be where the derivative doesn't exist. Dividing both sides by 4. That gives us 9 minus x to the 1/2 power equal 0. Now let's square both sides to get rid of that 1/2 exponent. So square that side. That gives us 9 minus x is equal to 0. Okay, x should be equal to 9. But, we just said, 9 can't be an inflection point. That's the end of our domain. Okay, the graph doesn't exist to the right of 9. So this here, really, this cannot be an inflection point. be an inflection point. All right, so this cannot be an inflection point. Let's cross that off. That's the very edge of the graph, right? So 9 can't be an inflection point because the concavity doesn't change. It won't change because it doesn't exist past 9. So let's see where the derivative is equal to 0 now. So we do 3x minus 36 over 4 times 9 minus x to the 1/2 power equals 0. Let's take the entire derivative now and set that equal to 0. Okay. Now, multiplying to both sides gives us 3x minus 36 equals 0. So 3x is equal to 36, x is equal to 12. Right? So this is this would be our inflection point. Except for one thing. I'm sure you guys have already got it figured out. 12 is bigger than 9. It can't be an inflection point. It's outside the domain. Now, so this is outside the domain of the original function. So x equal 12 cannot be an inflection point either. Right? Now, if you don't check the domain at the beginning of the problem, you're gonna assume that 12 is an inflection point, and it's not. So it can't be an inflection point. Okay, so let's see. What does this tell us now? All right. So 12, neither 12 nor 9 can be inflection points. So immediately we have no inflection points. So those would have been our inflection numbers. So no inflection points on this problem. But I tell you what, let's do. Let's check to see whether the graph is concave up or concave down. So let me erase this here. So we're going to see. So we know there's no inflection points. Well, let's check the concavity of the graph, though. All right. So let's check the concavity. So basically, what we want to know is this. You know, if you look at this graph, you know, now once again, this is not the graph of the original function. Okay, 9 is here. Okay, does the graph do this? Is it concave down, or does the graph do this? Is it concave up? So is the graph concave down? Okay, or is it concave up? So that's what we have to check. Now, to check that, we're going to pick us out a test value. Let's say maybe, and we'll see 0 would probably be a good one to check. Let's try 0 in the second derivative. And that'll tell us whether our graph will be concave up or concave down. And I'm just going to put this on a little number line, so like so. Put the 9 here, right? Okay, we'll put describe the second derivative on top and the function itself. So we're going to pick us out a test value. Let's try 0. Now you got to substitute 0 now into the second derivative, because remember the second derivative tells us the concavity, and that'll tell us whether the curve itself is concave up or concave down. So let's see. Now this is our second derivative. So the second derivative at 0 would be 3 times 0 minus 36. Now keep in mind, as we get this number, the actual number doesn't matter. The only thing that counts is whether it's negative or positive. That's all. Right, so minus 36 over 4 times 9 minus 0 to the 3/2 power equals. Now we got 0. We got negative 36 on top. Down the bottom will be 4 times. This would be square root of 9 is 3. 3 cubed is 27. So it'll be positive 27, which is negative. Now I'm not going to go ahead and multiply it on out. All I need to know, I got a negative divided by positive is negative. So the second derivative is going to be negative. That means the graph is concave down. Now, so you got to pick out a test value somewhere between negative infinity and 9. Substitute it into the second derivative. Now we've got the concavity of our function. All right, so we got the concavity of our function. Okay, well, that was a good problem. I like that. All right, so hopefully not all of them are going to be that complicated, but it's one thing when you're working with a second derivative, second derivative test, or whether you're looking for the inflection point, you're describing the concavity, you got to get the second derivative. Sometimes you can get it, within minutes or seconds, and sometimes you can't, like the problem we just did. Okay, let's try the actual second derivative test. Now the second derivative test, we're going to use it just like the first derivative test to locate maximum or minimum values. So let me erase this. All right, so this time let's use the second derivative test. And we'll do 1 or 2 problems here with the second derivative test. And And we'll see if we can use it to locate the relative maximum or minimum value. So, this is problem number 3. Let me pull it up here. This is our third problem. All right. Now, if you need to, go ahead and write it down. Go ahead and get it down, because I'm going to take this down in just a minute to give myself a little bit more room on my marker board here to work. All right, so it says use a second derivative test to find relative maximum or minimum. So this is number 3. So we're looking for relative max or min. All right, so what are our relative maximum or minimums? Now this time we have to use the second derivative test. So technically, if it doesn't tell you which test to use, you can use the first derivative test if you want to. So if you can easily get the second derivative test is good. But if it's going to take you a long time to get the second derivative, then you might as well go ahead and use the first derivative test. Because you basically have to do everything that the first derivative test does. And then you got to get the second derivative too. So like I said, it does have, if you can quickly get that second derivative, it's not too bad. All right, so we write our problem down here, and then we'll take this down. So we got f of x is equal to, so negative x to the 4th plus 4x cubed, okay, plus 8x squared. So this will be our next problem. All right. Now, once again, we're going to use the second derivative test here. Let's see if we get any relative max or min. I'm going to set this off. So give me a little bit of room here. So to get started, let's go and find the first derivative and the second derivative. So our first derivative, this is a little polynomial. Okay, also, you want to notice now the domain. Okay, the domain is all real numbers. Right? So this is a little polynomial. Polynomials are defined everywhere, right? So no restrictions on our domain. That's good, but you want to kind of be watching for that as you're doing some of these problems. Radicals and fractions, you got to be careful with. All right. Let's get our first derivative. Now the first derivative would be negative 4x cubed, okay, plus 12x squared plus 16x. So that'll be our first derivative. While we're at it, let's go and get the second derivative. All right. So the second derivative should be f prime x equals negative 12x. So negative 12x squared plus 24x plus 16. All right. So we got our second derivative. All right. Now, so with the second derivative test, we do everything that we did with the first derivative test. That means we got to find our critical numbers, because critical numbers would be possible minimum or maximum values. So let's get our critical numbers. Critical numbers. Okay, this will be where the first derivative is equal to 0, and where the first derivative does not exist. Okay. Now you got to watch out. So the second derivative test, you actually have to find the critical numbers, and to get those, you got to use the first derivative now. Remember, we're not checking the concavity this time. We want to find the actual minimum or maximum. Now, what's going to happen is this. We're going to get our critical numbers, and then from there, we're going to substitute that into the second derivative to see whether the graph would be concave up or concave down. But first of all, as you notice, the second derivative is a polynomial. There are no places where the derivative doesn't exist, so we don't have to worry about that. So let's set the first derivative equals 0. All right, so this would be, let's see, negative 4x cubed plus 12x squared plus 16x. Equal, erase this, okay, equals 0. Now we got to solve this equation for x. Now let's see, I've got a common factor here of, let's pull off a negative 4x. So negative 4x equals 0. Now we got a common factor. Now I want this first term here is going to be a second degree, so I want that first term to be positive. So I'm going to factor a negative off. Okay, that'll make this x squared minus, that's going to change the sign on the middle term. So minus 3x minus, so they'll change the sign on the last term on that trinomial also. So minus 4. Okay, now let's put this in factor form again. So negative 4x times, so set this equal to 0. We're going to factor, I'm going to solve this little trinomial by factoring it. That should go pretty quickly. The x squared will factor x and x, put 4 and 1. Right, now remember now, where your trinomial is, the last term of your trinomial is negative, that tells us the signs have to be plus and minus, so different signs. The middle term is negative, that means the 4 is going to be minus and the 1 is going to be plus. So we're going to do negative 4x is equal to 0, x plus 1 equals 0, x minus 4 equals 0. So we're going to end up here with x equals 0. That's our first critical number. Then we're going to do x equal negative 1 and x equal positive 4. All right, so we've got, let's count them. 1, 2, 3, 3 critical numbers. 3 possible minimum or maximum values. Now, if we were doing the first derivative test, we'd do this a wiggle graph, pick us out a test value, and from there that would tell us whether the graph is, the original function is increasing or decreasing, and we could get the minimum or maximum. Now, one good thing with the second derivative test now, we don't do a wiggle graph. All we have to do now, these are all possible minimum or maximum values. Now, to tell which, now we don't know whether they're a relative minimum or a relative maximum. Now, the second derivative will tell us that. All right, so with the second derivative test, now for the actual second derivative test, we have to take each one of these numbers and substitute them into the second derivative. So each of your critical number, let's plug these into the second derivative, and that will tell us whether or not it's a maximum or minimum. So remember now, if we take the 0, substitute into the second derivative, that tells us that the graph will be, if the second derivative is positive, it'll be concave up. If it's negative, it'll be concave down, and that'll tell us whether we're looking at a relative maximum or a relative minimum. So to get us started, let's take the 0, and let's substitute this into the second derivative. So remember, you're going to take the 0 here, and we're going to substitute it into the second derivative. And then we're going to do the negative 1 and the 4. And remember now, if we end up with a positive number, it'll be concave up. That indicates a minimum. If we get a negative number, that means the curve should be concave down and a maximum. So let's try the 0 first. So the second derivative at 0 gives us negative 12 times 0 squared plus 24 times 0 plus 16, which gives us positive 16. All right. Now, keep in mind, the actual number doesn't matter. What really matters is the fact that this is a positive 16. So this is positive. Okay, that tells us that this is going to be concave up. So concave up, that means the curve will do this. It's going to smile. So it's going to be concave up. Okay, that means at x equals 0, we're talking about a relative minimum. A relative minimum value. So x equals 0 is a relative minimum. Okay. See how that's going to go? So all you do is take that critical number now. Don't do a wiggle graph. You're going to take the number itself and substitute it into the second derivative. All right, so since the second derivative is positive, at that particular critical number, the graph is going to be concave up, and that indicates that we're looking at a relative minimum. Okay, let me try the next critical number now. Okay, now let's try the negative 1. All right, so the second derivative at negative 1 would be negative 12 times negative 1 squared plus 24. So 24 times negative 1 plus 16. All right, and let's see what we get here. It'd be negative 1 squared would be negative 12 minus 24, okay, plus 16. Okay, this will give us what? Negative 36 plus 16, which is negative 20. All right. So remember now, the actual number itself doesn't really matter. The only thing that matters is that it's a negative number. So this is negative. Okay, that tells us right there that this is going to be concave down at negative 20. So the curve is going to do this. Now, if it's concave down, that means the top of the curve here is going to be a maximum value. So this will be a relative max, okay, at x equal negative 1. So a relative maximum at x equal negative 1. So this one's a relative minimum. This is a relative maximum. All right, let's check the positive 4. Let's see what we get here. So let me erase this. So let's check the positive 4, and let's see what we get. So positive 4. Okay. Okay, so this would be the second derivative at 4 would be negative 12 times 4 squared plus 24 times 4, okay, plus 16. Okay, which will give us negative 12 times 16. Let me get my calculator here. I want to try to save a little bit of time. So negative 12 times 16 gives us negative 192. Okay, plus 24 times 4, which is 96. Okay, plus 16. Now 96 plus 16 gives us 112. So it'll be negative 192 plus 112. Okay, combining these two now, minus 192 gives a negative 80. So negative 80. All right, so once again, the actual number itself doesn't matter. All that matters is this negative. Okay, that means that this problem will be concave down. Equal 4, so that's right. So concave down. Double check. All right, so in my notes I only did the 0, the negative 1, and the 4. So this would be concave down. All right, so concave down. So you're looking at this right here. So this would be a relative max. So relative max. Let me just double check this now to make sure that I'm right here. So I'm going to factor this. This will factor is 4 and 1. Okay, so we have x equal negative 1, x equal positive 4. So x equal positive 4, we're substituting this into the second derivative, okay? So relative max, and let's see, double check, so it'll be negative 12x squared plus 24 times 4, okay, plus 16, so this is our second derivative, so that's right. And let's see, evaluating this, let's just check my calculations again. This would be a negative 192, so it's a positive 4. So negative 12 times 4 squared, so times 16. Okay, plus 96 times, so plus 24 times 4. Okay, plus 16. That gives us negative, let's see, she give me, yeah, negative 80. All right, so we're looking at a relative max at x equal 4. Okay, now let's try one more example. So let's, let me go ahead and erase this. So one more example. And let's see now. Okay, now this time let's try a trig function, all right? So let's try a trig function. Okay, see we've done a radical. So we've done a radical, we've done a couple of polynomials. Okay, let's try this problem right here now. So let's try this problem right here. This will be number 4, this will be our last example, all right? So we'll do one more. Now this time, we're going to use the second derivative test again to find any relative maximum or minimum. All right, so number 4. So we'll do any relative, any maximum or min. Okay, now the actual function here, we have f of x is equal to x plus 2 times cosine x. So cosine x. So x plus 2 cosine x. There we go. So this is our original function. Now we're going to do this over the open interval from 0 to 2 pi. So this will be over the interval from 0 to 2 pi. All right. Now keep in mind now where the interval is open, 0 and 2 pi cannot be minimum or maximum values. All right. So it's going to be, so we don't have to worry about checking the endpoint on this problem here. All right. So let's see what we get. Now we're going to use and we'll take this off. Alright, so let's use the second derivative test. Let's see what we get here. Now, let's go and get the first derivative to begin. Alright, so the first derivative here would be, so the derivative of x is 1. The derivative of cosine is negative sine, so it would be negative 2 sine x. And let's go and get the second derivative. So the second derivative, now the derivative of 1 is 0. The derivative of sine x is cosine x. So this would be negative 2 cosine x. Okay. Right, now we've got the first derivative and the second derivative, right? So we have both of those. Now one thing I want to do before I go any further, I've got my orange Pike Central hat. So I saved this for last. I didn't wear it during the entire video, but I look good in it. So this is my orange Pike Central, actually a baseball hat, I believe. Right. Now we got our first derivative, we got our second derivative. So to start us off, let's get our critical numbers. All right, so this will be where the first derivative is equal to 0 and where the first derivative does not exist. All right. Now, one thing we notice about the first derivative is in terms of sign. All right, so it has sign in it. Sign is defined everywhere, so there are no values where the derivative doesn't exist. We don't have to worry about that. So now let's take the first derivative and set it equal to 0. So 0 equals 1 minus 2 sine x. And let's see if we can solve this for x now. This gives us negative 1 equals negative 2 sine x. Dividing both sides by negative 2 gives us 1/2 equals sine x. All right. Now, to solve this equation, all right, so sine x, sine would be our y value, right? So if you remember your unit circle, all right, so like so. So sine would be, so sine x, so 2 sine x, this would be, so sine would be our y value, so this would be right here, would be 1/2. Right, so we're talking about this number here and this number here, so it'd be pi over 6. That'll be the square root of 3 over 2 and 1/2. And then here would be what, 5 pi over 6. That'll be a negative square root of 3 over 2 and 1/2. Okay. So negative square root of 3 over 2 and 1/2. So we got two solutions for our critical numbers. So as we look at 1/2 x, 1/2 equals sine x. Okay, x is going to be equal to pi over 6 and 5 pi over 6. All right, so two critical numbers. Now keep in mind, each of those could be possible minimum or maximum values. So possible minimum or maximum. All right. Now, if we were doing the first derivative tests, we could, all we have to do is put these two critical numbers on a wiggle graph, pick out a test value, and we would check them in the first derivative. But we're going to use a second derivative test here. Now, for the second derivative test, all we have to do is we'll take the actual critical numbers, right, and we're going to take those and substitute them into the second derivative. So let's do the second derivative test here now. So the second derivative test. All right. So we'll take each of these numbers now and plug them into the second derivative. And let's see if that number is negative or positive. That'll tell us whether or not our critical number indicates a relative maximum or a relative minimum. So let's do the pi over 6 first. Now this will be, so let's see, x equals pi over 6. So substitute this into the second derivative. So the second derivative of pi over 6 would be negative 2 times cosine pi over 6. Now say cosine pi over 6 is the square root of 3 over 2, so it would be negative 2 times the square root of 3 over 2. These will cancel, which gives us negative square root of 3. All right, now, since the second derivative is negative, all right, so this is negative, okay, that tells us the curve is concave. So concave down, so like so, and looking at a relative maximum value at pi over 6. All right, so we've got a relative max, so a relative maximum at x equal pi over 6. Now, to get the actual number, now this would be the x value, all right? Now, to get the actual number, you'd have to take the pi over 6 and substitute it back up into the original function. Now, I'm not going to do that. I'm just getting the x value here. But, very easily you can get the actual point, well, we wouldn't need to do that with the critical number, but that would give us the actual maximum minimum. So I'm not going to do that here. But let's check the other critical number now. Let's see if we have a relative maximum or minimum at this number now. So we have 5 pi over 6, and this would be the second derivative. So 5 pi over 6 would be, and let's see, it'd be negative 2 cosine now, 5 pi over 6, okay, which is negative 2 times, now see this is cosine. Cosine would be the x value, would be negative square root of 3 over 2. Okay, these would cancel, which makes this a positive square root of 3. Now since this is positive, that indicates it's going to be concave up. Concave, okay, up, so like so, and that indicates a relative minimum. Right, so we have a relative minimum, okay, at x equals 5 pi over 6. So one thing with the second derivative test, you don't you don't have to do the wiggle graph. You don't have to pick out the test values. So with the second derivative test, you got to remember now, you use the actual critical numbers, and you test them in the second derivative. So you're going to take the critical number itself, and you got to plug it into the second derivative, and that tells you whether it's concave up or concave down, and then that tells you whether you have a relative maximum or minimum value. All right, so this is the second derivative test. We looked at two examples, polynomial and a trig function. We looked at a problem or two where we had looked at discussing the concavity of a function, the intervals where it's concave up or concave down, and we looked at a few problems we had to find the inflection point. So hopefully this helps you a little bit. Like I said, the second derivative test is a very a good test. Two disadvantages though with the second derivative test. Number one, it doesn't work all the time. If the second derivative is 0, that doesn't tell you whether it's concave up or concave down, so it doesn't always work. And number two, you got to get the second derivative. Right? So if the first derivative is hard, the second derivative would be much harder. So the second derivative test does have some disadvantages, but if you're going to find the inflection point or describe the concavity, you have to use the second derivative.